Good morning, everybody. In today's lecture, we're gonna talk about the concept of flow nets. In other words, two-dimensional water flow in soil. Water flow in soil is not only vertical or horizontal, and it is not uniform over the whole area perpendicular to the flow of water. In these complicated cases, groundwater flow is usually estimated by means of graphs referred to as flow nets. To describe the principles of flow net, let us consider a case where sheet pile is driven into the permeable soil to ease the process of excavation. The head difference between two water levels causes water to flow from upstream to downstream, and the flow paths followed by water named as flow lines as illustrated in the figure. Since impermeable surfaces such as AB and DEF are considered to be flow lines. In this case, there are three flow lines as illustrated in the figure. Numbering of flow lines starts with 0. Flow lines are needed to be more or less drawn parallel to each other, and the area confined by two flow lines is called flow channel. 3 or 4 flow channels can be sufficient for most of flow nets construction. For example, there are 3 flow channels in the figure. Lines connecting points with the same total heads are named as equipotential lines. These lines must intersect flow lines at right angles, as shown in the figure here. In this way, near squares or rectangles are formed, which are termed equipotential drops. Submerged permeable surfaces such as CD and FG, as you see in the figure, are regarded as equipotentials. In this case, there are 7 equipotential drops in each flow channel in the figure. In the construction of flow net, all scaled cross-section is originally drawn, establishing all the boundaries owing to side, structure, etc. After that, a series of successive trials is needed with the ultimate purpose of drawing a flow net where all parts comply with the rules stated earlier. In order to calculate the flow rate, let us consider a flow channel as given in the figure, and let H1, H2, H3 be the piezometric levels corresponding to the equipotential lines. And let delta Q be the flow through the channel per unit depth. According to Darcy's law, delta Q is equal A times K times I. A is the cross-sectional area of the flow channel with unit depth as illustrated in the figure. K is the hydraulic conductivity of soil, and I is the hydraulic gradient. Now, referring to the figure, delta Q, which is the flow rate, will be the same for each element defined by flow and equipotential lines. With this approach, we get equation 1. For each section, if you notice, the hydraulic gradient and the area different, but the delta Q, which is the flow rate, as stated, is the same. If now the flow elements are drawn as squares, then the width and the length of the elements will be the same. In this case, we get the head laws between each successive pair of equipotential lines as given in equation 2. In the equation, small h is the head difference between the upstream and downstream sides, and ND is the number of potential drops. Equation 2 shows that the loss of head between any two successive equipotential lines is the same. Now, integrating equation 1 and equation 2, we get delta Q in terms of K times H over ND. If there are n flow channels in a flow net, then the rate of flow is obtained as NF times delta Q. If rectangular elements are used in the flow net, the flow rate is obtained as given in the equation here, where NF is the ratio between the width and the length of the elements. In nature, most soils display some degree of anisotropy. To take account of soil anisotropy regarding hydraulic conductivity, we must adjust the flow net construction. To sketch the flow net in this case, the following procedures are needed. In step 1, a vertical scale for drawing the cross-section is chosen. In step 2, a horizontal scale is chosen such that horizontal scale is equal to square root of kz times kx times vertical scale. In step 3, with the scales chosen in steps 1 and 2, the vertical section through the permeable layer parallel to the direction of flow is plotted. In step 4, the flow net for the permeable layer on the section obtained from step 3 is drawn with flow lines intersecting equipotential lines at right angles and the elements as near squares. The CP rate per unit length can be worked out by the following equation given here, where Kz is the permeability in vertical direction, Kx is the permeability in horizontal direction, H is the total head loss, Nf is the number of flow channels, and Nd is the number of potential drops. It is important to note that when the flow nets are plotted in a transformed sections, the flow lines and equipotential lines are orthogonal. Nevertheless, when they are redrawn in a true section, These lines are not at right angles to each other anymore. For water pressure at any point within the flow net construction can be calculated. For these, let us consider a case where water flows from the upstream to downstream beneath a dam as shown in the figure. After constructing flow net, let us choose point A as given in the figure somewhere here. Initially, we need to select a datum. In this figure, the datum is the downstream water level because it is the lowest water level. And the second step, the elevation hat at point A is determined, which is minus age AE. It is negative because point A is below the datum as shown in the figure. Now then, the total head difference between upstream and downstream is H or HW. As the water flows under the dam from upstream to downstream, the total head will gradually decrease. The greatest value of total head is at the ground level on the left before the water flow begins, and the lowest value at the ground level on the right hand side after the water passes the last equipotential drop. The total head will lessen by a certain value after passing an equipotential drop. This value is known as the total head loss, and it is calculated as HW over ND. To arrive at point A, the water would pass 1.5 equipotential drop, which will decrease the total head by a value of 1.5 delta H. The total head in this case at point A will be HW minus 1.5 times delta H. The pressure head at point A is calculated as HAT plus HAE. Eventually, the pore water pressure at point A equals HAP times unit weight of water. When there is a steady state water flow under a huge engineering structure like a dam, the water seepage will result in an uplift force as shown in the figure, which can weaken the stability of the structure. The average uplift force per unit length of dam based on the pore water pressure along the dam's foundation can be calculated using this equation given here, in which HPA and HPF are the pressure heads at the edges of the dam, and LAF is the distance between points A and F. To work out the uplift force which acts on the dam, we will first estimate the pressure heads at points A and F, and then, using the equation, uplift force can be calculated. The elevation head for both points A and F is 0. To attain point A, the water flow would pass one equipotential drop, which will lessen the total head by a value of 1 times delta H. So the total head at point A is equal to H minus delta H. The pressure head at point A will equal, in this case, HTA minus HE. To arrive at point F, it takes about 6 equipotential drops. Therefore, the total head at point F is H minus 6 times delta H. The pressure head at point F will equal, in this case, to HTF minus HE. Here you have a practical example to better understand what I have explained so far. A dam, as shown in the figure, built on alluvial soil with the average coefficient of permeability of 10 to the power of minus 6 meter per second. So you are asked A, to sketch a flow net and compute the flow rate in cubic per day. B, to determine the pore water pressures at points B and C on the cutoff wall. By the way, cutoff wall or cutoff curtain, as shown in the figure, is formed by grouting the mixture of bentonite and cement into the ground to a certain depth, or simply formed by driving sheet pile, the purpose of which is to lengthen the flow path, thus mitigating the rate of flow. And finally, C, to determine the uplift force beneath the dam. In solving this problem, we first need to draw the dam to scale and identify the impermeable and permeable boundaries. In the figure, AB and EF are permeable boundaries because water can easily enter and exit these surfaces. So they are equipotential lines. On the other hand, B, C, D, which are the surfaces of sheet pile wall, DE, which is the base of concrete dam, and GH, which is the surface of rock layer. They are all impermeable boundaries because water cannot penetrate in them. So they are flow lines. Now thereafter, a flow net can be constructed as shown. To construct flow net properly, I'll give you some tips. Draw about 3 flow lines and then draw a suitable number of equipotential lines. Keep in mind that flow lines intersect equipotential lines at right angles, and the area between 2 consecutive flow lines and 2 successive equipotential lines is nearly a square. Use a circle template to assist you in determining the square. Modify, add, subtract flow lines and equipotential lines until you get curvilinear squares. The question is, if I practice this example on my own, I may draw a flow net with 5 flow channels, not 4. Is my answer incorrect? No, it is not. Your answer may be somewhat different, but it doesn't mean that it is wrong. The point is, when we draw the flow net, the equipotential drops should be more or less in square shape. If you use more flow lines, it means that you need to increase the number of equipotentials to keep the square shape of the drops. Consequently, the ratio between the number of flow channels and the number of equipotentials would not be very dissimilar. Let us calculate the flow rate. To do this, we need to select the lowest water level as the datum. According to the figure, the lowest water level is on the downstream side as shown. In this case, the total head between two water levels is 3 meters. Since we have the flow net construction, we can determine the number of flow channels and the number of equipotential lines, which are 4 and 10 respectively. Now, the rate of flow can easily be obtained using the equation given here. If we put all the related values in their places, then we get the rate of flow of water as 0.104 cubic meter per day. It is important to note that the flow rate is calculated for 1 meter length of wall. Now let us determine the pore water pressures at point B and C. To do this, we first should find the pressure heads at point B and C. For these, the elevation heads and the total head loss should be determined. Elevation head at point B is -1, at point C is -5 because they are below the datum chosen. And delta H, which is the head loss, is 3/10. 3 is the head difference between two water levels, and 10 is the total number of equipotential line. Therefore, delta H is equal 0.3. Now then, as there are 0 and 3.5 drops to points B and C, the total heads at point B and C will be 3 meter and 1.95 meter as calculated here. Accordingly, the pressure heads at point B and C will be the difference between total heads and the elevation heads. So the pressure head at point B is 4 meter and at point C it is 6.95 meter. As a result, the pore water pressures at point B and C are the multiplications of the pressure heads and the unit weight of water. Thus, the pore water pressure at point B is 39.24 kilonewton per square meter, and at point C it is 68.18 kilonewton per square meter. As a final step, let us compute the uplift force under the dam. As stated before, we should first find the pressure heads at point D and E. To do this, we need to find out the elevation heads and the total head loss. The elevation head at point D is -1 and at point E is also -1 because they are below the datum chosen. And delta H is the head loss calculated before. Therefore, the total heads at point D and E will be 1.40 meter and 0.3 meter. Accordingly, the pressure heads at point D and E will be 2.40 meter and 1.3 meter. Since the length of the dam is 10 meter, the uplift force acting under the dam will be around 168.73 kilonewton per meter. Notice that we have calculated the uplift force based on 2 points, which are the end points of the dam. If you like, you can divide the length of the dam into several distances and determine the pressure or water pressure at each point, then calculate the uplift force more accurately. Now, take into consideration the case of a homogeneous isotropic embankment dam built on an impermeable foundation as shown in the figure. The impermeable boundary AB is a flow line and CD is the required top flow line. At every point on the upstream slope AC, the total head is constant as stressed before. Therefore, AC is an equipotential line. If the downstream water level is taken as datum, then the total head on equipotential AC is equal to H, the difference between upstream and downstream water levels. The discharge surface BD shown in the figure is the equipotential line for zero total head. At every point on the top flow line, the pressure is zero. So total head is equal to elevation head, and there must be equal vertical intervals between the points of intersection between consecutive equipotentials and the top flow line as illustrated. It is important that a suitable filter ought to be set up at the discharge surface in an embankment dam as displayed in the figure. You may ask why the filter is needed. The goal of the filter is to hold the seepage entirely within the earth dam. Water seeping out onto the downstream slope would bring about the gradual erosion of the slope. The result of such erosion can be very serious. For example, in 1976, a leakage was noticed close to one of the abutments of the Teton Dam in Idaho, USA. Seepage was finally observed through the downstream phase, and within 2 hours of this appearance, the dam gave in catastrophically. Filters must meet some certain fundamental requirements. The voids must be small enough to prevent particles from being carried in from the surrounding soil. The hydraulic conductivity must be high enough to provide the free drainage of water coming into the filter. The capacity of a filter should be so much so that it doesn't get fully saturated. In addition, the filter must stay stable under the unnaturally high hydraulic gradient. The following criterion has been suggested for the acceptable filter performance. D sub 15F over D sub 85S should be less than 5, where D sub 15F and D sub 85S refer to the filter and surrounding soil respectively. Nevertheless, in the case of filters for fine soils, the following limit is recommended for the filter material. D sub 15 should be less than or equal to 0.05 millimeter. To make sure that the permeability of the filter is high enough to permit free drainage, it is recommended that D sub 15F over D sub 15S should be greater than 5. Most filters are multi-layers of sand and gravel. These filters are difficult to construct, and their efficiency is easily endangered by even a small amount of fines. Geotextiles, a permeable polymeric material, have replaced soil filter in many construction applications. Let's take a quiz to recap what we have learned so far. Sketch the flow net for the soil mass given in the figure here and answer the questions. Shall we sketch the flow net together? Okay, then we start with flow lines and then equipotential lines. Make sure that equipotential lines intersect flow lines at right angle, forming near square areas. Now, question 1. How many flow lines are in the flow net of the figure? How many? 4. Very good. Now, let's count together. 0, 1, 2, 3, 4. We know that impermeable surfaces or boundaries are considered to be flow lines. Question 2. How many equipotential drops are in these flow net? Again, starting with 0, count down. How many? No. Be careful. Permeable boundaries are considered to be equipotential lines. In this case, we have how many? No. We have 4 equipotential drops. Again, let's count together. 0, 1, 2, 3, 4. So the answer is B. Question 3. What is the difference in total head that causes the flow of water? This is easy peasy Japanese. The answer is A. Very good. 15 centimeter. Question 4. What is the total head loss for each equipotential drop. Now, you know the head difference, the number of equipotential lines and the number of flow lines. Which one? 15 over 4. Well done. The answer is C. And the final question, what is the total head at point O as shown in the figure? I give you some time to figure out. Don't worry. No answer yet? Okay. I'll give you the answer. The answer is A, 7.5. You do this exercise on your own. Question 6. Which of the following statements is not correct? Which one? D. Yes, the answer is D. Flow lines are lines with the same total head. Very good. Question 7. Which of the following statements is not correct? Which one? No, it is not. The answer is C. The rate of flow in a flow channel is not constant. And the final question, which of the following statements is correct? Which one? Yes, the answer is B. The velocity of flow is normal to the equipotential line. Jolly good. That's all, folks. I appreciate your interest and participation. Have a nice weekend. Hope to see you again.